Morning, everyone. Okay, also, these are also I will clarify doubts. Let's go for the integrals, different various linear mass densities, row with linear mass density, very linear mass density, and then let's find out some situations where let's come across some situations where yeah, all right. So, you have any specific doubts, or should I go with variable mass density? Because that's going to be useful in our next chapter as well. So, before we begin next chapter, let us quickly revise the variable mass density, how to deal with that, how to frame an integral and how to deal with variable mass densities. All right, or do you have any specific doubts, students? If you have any specific doubts, we'll go with that, or I'll go with variable mass density. So, students, what is that you need? Should I go with variable mass density, or you have any specific doubts? Students, are you all there? Good morning, Vignesh, Shivani, Asita, Sophian, and Gayatri. You can unmute and speak.
So we can continue with variable densities.
Variable density, right? But today evening, we're going to start the new chapter. Okay, I've got a row. On a frictional surface, where the coefficient of friction is mu. All right. First, let's say linear mass density is constant, lambda naught. So mass is m, length is l. M by l is constant, lambda naught. I have to find the relation between mu and lambda naught such that the rope remains in equilibrium. So what do I do? The force acting on this part, let's say this is x, and this is l minus x. So force acting on this part, hanging part, is gravitational force, which is to be counterbalanced by tension
Frictional
over
force.
here, and that tension is equal to the limiting friction over here. If it's on the verge of slipping, if it's on the verge of slipping, this gravitational force should be equal to the limiting force over here. What is the limiting friction? Mu times n. So let's find out what is the mass of this, students. If x is the length, lambda naught is the linear mass density. What is the mass of this hanging part? Lambda naught x is the mass of the hanging part times g is mg. Now that should be equal to mu times n. N is how much? Mg of this part on the table. which is mass is lambda naught into L minus x times g, mg, mu mg. So g gets cancelled out, lambda naught gets cancelled out. So I'll have x is equal to mu times L minus x. So I'll have x is equal to x into 1 plus mu is equal to mu L. So x is equal to mu L by 1 plus mu. So I got the length which should be hanging such that that's on the verge of slipping. Any length more than this length, mu L by 1 plus mu, it will slip. Any length less than this, it will not slip. When it's less than this, that is the friction is not limiting, but it's static friction. If the hanging part is less than this length, let's say x naught. If x is less than x naught, then the friction over here is not limiting, but static. But if x is greater than x naught, then the friction over there will be kinetic. For x is equal to x naught, the limit friction is going to be limiting static friction. All right, because its linear mass is constant, I'm directly multiplied with the linear mass density to length. I got mass. Linear mass density to length. I got mass. Mg is equal to mu mg. Solving further, I got x naught. Now, when x is less than x naught, the hanging part is less than x naught, less than the limiting value. My friction over there is limiting static, less than limiting static friction, which is static friction. If x is greater than x naught, it will start slipping, and the friction over there will be kinetic friction. Now, let's say x is greater than x naught, and I have to find the acceleration of the string. How do I find the acceleration of the string? For x greater than x naught, lambda naught x minus mu lambda naught into L minus x is equal to total mass into acceleration. What is total mass? Lambda naught into L into acceleration. So lambda naught gets cancelled out. So I'll have acceleration is equal to x minus mu into L minus x by L. Sorry, g over here, g over here, g over here. So that's the acceleration when x is greater than x naught, and it's slipping. The friction cannot anymore support the hanging part, because of which the rope will start slipping. Is it clear, students? What did I do basically? I have just written F is equal to ma. Net force equal to mass into acceleration. What is the net force? Mg over here, mu mg is the friction, kinetic friction. Supporting force minus opposing force is equal to mass into acceleration. All right. Now let us see if what happens if there is a variation in density. I'll take density variation to be e power minus x by L. All right. Last time we have taken lambda naught is equal to lambda naught into x by L, which was linearly varying, and we have done some. We've also found out for what length is the mass half of the total mass, or for what length is the mass equal to the remaining portion. All right. Now let us do it for exponential variation. You can do it for any variation. It's just a matter of integration. So let us say the variation is not constant. I mean, the linear mass density is not constant, but varying with lambda is lambda of x. Okay, it could be lambda naught into x by L. It could be lambda naught into e power minus x by L. or any other function. Okay, but we have done with this function, so we'll go with this function now. In this case, let us find out the total mass of the rope. How do I do that? Let's find out the total mass of the rope first. So at a distance x, let's say origin is here, x is varying like this, and your mass is varying like this. That means it's thinner here, thicker here. Sorry, thicker here, thinner here. My exponential function is varying like this, right? So it's thicker here, thinner here. So more mass at the initial portion of this x, and as I go ahead, as x increases, my mass becomes, density becomes lesser. So it becomes thinner or less denser. Not literally thinner, all right? Rope may be of the same thickness, but density is decreasing, all right? So density over here is lambda naught, where x is equal to L. Density over here is lambda naught by E, when length is L. All right, that's how the density is varied. Now, I chop this into infinite number of infinitesimal pieces. So at a distance x, I consider element dx. The variation of density along this length dx is presumed to be constant. I take dx to be so small that I can treat lambda to be constant in that region. Realize the point. I'm making dx to be so small, I'm taking dx to be so small that I can treat lambda to be constant in that region, so that I can write dm, mass of that small part, small infinitesimal part, dm, to be equal to lambda into dx. All right, I cannot write this lambda into L, but because length is so small that my lambda is constant over there, I can write lambda into dx. So lambda is how much? Lambda naught into e power minus x by L into dx. So m will be equal to integral 0 to L. All I have to do is sum up all the infinitesimal parts. Sum up all the parts. There are so many parts, infinitesimal part, infinite number of infinitesimal parts. I have to sum up. Summing up infinite number of infinitesimal parts is one integration. I get summation integral lambda naught e power minus 12 dx from 0 to L. Now I have to integrate this. Lambda comes out integral e power minus x by L dx from 0 to L. Now integral e power ax is e power ax, integral is dx is e power ax by a. Just to verify, if I differentiate this, I should get this. What is the derivative of e power ax by a? E power ax by a into a. A gets cancelled out. I'll have e power ax. So derivative of this should be this. So integral of this is this. That's fine. So integral of this would be lambda naught by lambda naught into e power minus x by L by minus 1 by L under limit 0 to L. I substitute the upper limit. e power minus 1 by L negative of that. So that becomes lambda naught by 1 by L, right? So lambda naught into L into 1 minus 1 by E is my total mass M. Look at this, students. My mass M is not lambda naught into L, but there's another factor, additional factor, multiplication factor, which is 1 minus 1 by E. If lambda were constant to be lambda naught, then I would have lambda naught into L as my mass, but because it's varying, I've got 1 minus 1 by E as a multiplicative factor. All right. Did you understand how I got the mass? Now, if I give you some other function, will you be able to do? If I give you some lambda of x instead of e power minus x by, if I give you some other function, how do we do? I'll write dm. I'll chop this into infinite number of infinitesimal pieces. I'll take dx to be so small that I can treat that lambda to be constant in that region. Because it's constant, I can write dm is equal to lambda times dx, where lambda is, I substitute the function. So m will be equal to summation of all the particles, all the small elements. Summing of all the elements will give me total mass. Is this clear, students?
Yes, sir.
Okay. Now let's, just for a simple exercise, let's find out that length of the door for which mass is half of the total, or that length of the row which has mass equal to the remaining portion of the row. That means this mass should be equal to this mass. This would be equal at L by 2 if the lambda were constant. But because lambda is not constant, this is heavier, this is thicker, this is denser, this length should be less than L by 2. Common sense says this length should be less than L by 2. So solution, when we solve the whole problem, we should get L to be less than L by 2, x naught to be less than L by 2, right? That makes sense. So let's find out that x naught. So what do we do now? So I've got, when I integrate from 0 to x naught, lambda of x dx, this should be equal to, when I integrate from 0 to, sorry, x naught to L, this should be the condition. Or this should be equal to half of integral 0 to L lambda of x dx. I can use either these two or these two or these two to get x naught. Do you understand this equation? Mass of 0 to x naught, this portion, should be equal to the remaining portion. That's what these two mean. Or what does this mean? This is half of the total mass. When I integrate from 0 to L, your total mass, that should be half of the total mass. So can you now go ahead and tell me what is the value of x naught? Okay, let's do it together. I'll use these two first. So I'll write integral 0 to x naught lambda naught into e power minus x by L dx should be equal to integral 0 to L lambda naught into e power minus x by L dx. So lambda naught gets cancelled out. So I integrate this e power minus x by L is e power minus x by L by minus 1 by L, e power ax by A under limit 0 to x naught. Now this is equal to e power minus x by L by minus 1 by L under limits x naught to, sorry, 0 to L and half of this one. So 1 by L gets cancelled out. Can you further substitute the limits and let me know? Ultimately, I want x naught. Yeah, go ahead and substitute. I mean, substitute the limits and simplify and let me know what is x naught. Upper limit e power minus x naught by L minus, okay, I've got negative here. So what I'll do, no negative, right? Minus is 1, minus 1 by L, minus 1 got cancelled out. So I have e power minus x naught by L minus 1 is equal to half of e power minus 1 minus 1. Yeah, further simplify. Are you all doing?
Yes, sir.
Okay. Further simplify this. Multiply this by 2. Further simplify. Okay, now go ahead. This is 2 minus 2 minus 1. 2 goes over there plus 1. So e power minus x naught by L is equal to 1 plus e power minus 1. So this is nothing but 1 by 1 plus e. 1 plus 1 by e. This is into 2. Yeah, take logarithm on both sides. Log on both sides. You'll get,
So, so,
Yes.
I've got the answer in different way by like L naught by x ln by x naught equal to log 2e by 1 plus e.
Right, right, right. X naught is equal to L naught into, or X is equal to L into, sorry, X naught is equal to L into log of 2e by 1 plus e, right?
Yes.
Yeah, that's it. Now we should get the same answer if I use these two as well. Let's quickly check we are getting the same answer or something wrong we might have done. All right, I don't trust my calculations. I mean, I don't trust my simplification. But if you all also got the same answer, then that's right. All right, that means what I've done is right. All right, let's check with these two. We have checked with these two, right? Let's check with these two. So we've got integral lambda naught into e power minus x by L dx is equal to integral lambda naught into e power minus x by L dx when x goes from 0 to x naught, that should be equal to x naught to L minus x naught. Sorry, x naught to L. So lambda naught again gets cancelled out. So I'll have e power minus x by L by minus 1 by L under limit 0 to x naught should be equal to e power minus x by L by minus 1 by L under limits x naught to L. So this 1 by L gets cancelled out. You understand this equation? My mass from 0 to x naught is equal to mass from x naught to L. All right. If this were constant of data mass density would be constant, then I would have L by 2 to be the answer. But now I'm getting initial portion mass 0 to x naught should be equal to the remaining portion mass. Mass of the remaining portion is x naught to L, integrating from x naught to L. Mass of the initial portion is, the first portion is x0, integrating the density from 0 to x naught. All right. Now I get e power minus x by L, x naught by L minus 1 should be equal to e power minus 1 minus e power minus x naught by L. So this comes over here, this goes over there, 1 goes over there. So I get 2e to e power minus x naught by L is equal to e power minus 1 plus 1. We are again getting back to the same equation. So I've got 1 by 2. So which is e power x naught by L is equal to 1 plus e by 2e. So x naught by L is equal to log of 2e by 1 plus e. Oh, sorry. Not seen, not visible. So x naught is equal to L times log of 2e by 1 plus e. We got the same answer again. Whether I use the first term in the last term or the first term in the second term. All right. See, but physically we meant different thing. We said mass of this portion is equal to mass of this portion, which is nothing but equivalent to say is mass of this portion is half the total mass. All right. We got the same thing. We got the same result. All right. Now let's do one thing. Let us apply some force over here and find the tension as a variation of x. Some force F naught is applied. I have to find the tension, how it varies with x. You can also find the acceleration of the string. All right. Acceleration of the string would be net external force by total mass. What is the net external force acting on the string? Only F naught. F naught by total mass is the acceleration of the string. Now, what is the total mass? I integrate that from 0 to L. I integrate this density from 0 to L. I mean, with respect to x. All right. Now, F, so acceleration is F naught by total mass, which is 0 to L, e power lambda naught into e power minus x by L dx, which is equal to F naught by lambda naught into 1 by integral e power minus x by L dx from 0 to L. Can you simplify this further and tell me what's the acceleration? Evaluate the integral. Simplify and tell me the acceleration. Quick.
X naught equals to
Sorry?
X naught equals to L log 2 by E.
No, which one are you doing? You're still in the last problem, right? We have moved on to the next problem. I'm asking you to evaluate this one. That log of 2 plus 2e by 1 plus e is done. You got the answer and that's the right answer. I'm asking you to evaluate this integral now.
One by D X
Yeah, so what is it? F naught by lambda naught into 1 by e power minus 1 by minus 1 by L under limit 0 to L. So minus 1 by L goes to the top. I can remove this minus sign. I can flip the limits L naught to 0 and this L goes to the top. It becomes 1 by lambda L. This is my acceleration. So I substitute the limits from L to 0. Now substitute the limits. I'll get F naught by lambda naught into L into 1 minus 1 by E. Is my acceleration. Now this acceleration is going to be useful in the next step. Do you all understand how I got the acceleration? How I integrated it? Integral 0 to L e power minus x by L dx is equal to e power minus x by L by minus 1 by L under limit 0 to L. This negative sign over here, I'll remove it and I flip the limits. L to 0. This 1 by L becomes L here. L goes to the top, numerator. I substitute the limits now. When I substitute limits e power 0, it is 1. When I substitute L, x is equal to L, e power minus 1, which is 1 by E. So L into 1 minus 1 by E is my total mass. Lambda naught into L into 1 minus 1 by E is my total mass. F by total mass is the acceleration. Alright. Okay, this is just a mathematical part. Now let's come to the required tension at a distance x from the end O. Alright. Can you remember this? Can you note down this? A is equal to F naught by lambda naught into 1 minus 1 by E. Alright, I'll ask you after a while. You tell this to me. I'm erasing it right now. After a while, you let me know what is the value of acceleration. Acceleration is F naught by lambda naught L into 1 minus 1 by E. Now let's go for tension in the string. What I do at a distance x, I section this into two parts and I draw the FBD. This is my tension T here. This is F naught and this is tension T on a frictionless surface. So you'll have normal reaction and mg, normal reaction and mg, which are not coming into play because there is no friction. Because there is no friction, normal doesn't matter. If there were friction, normal would matter, and I would consider the normal reaction as well. But right now, I'm just considering only the horizontal forces. And what is the acceleration of this block? This part, A. Acceleration of this part is also A. So MAD and FAD are complete. So I'll write T is equal to mass of this into acceleration. What is the mass of this? 0 to x, lambda naught e power minus x by L dx. I got mass into acceleration. What is the acceleration we got?
F naught by lambda naught L into 1 minus 1 by E, sir.
Into 1 by
Right. Now that's my tension as a function of x. Now all you have to do is evaluate this integral and go ahead. Can you evaluate this integral now? Lambda naught gets cancelled here. This exponential is a very important function, students, in physics. This exponential function, especially the decreasing exponential, is very important. E power minus x by L is very important. Alright, you should be able to handle e power minus x by L with ease. Alright, so what are we getting? So integral 0 to x e power minus x by L by 1 minus 1 by L under limit 0 to x times f naught e by L into e minus 1. Now there is negative sign here. I'll flip the limits. I'll remove the negative sign and flip the limits here. It becomes x to 0. And there's 1 by L here, that gets cancelled out. So all I'll have is 1 minus 1 by e sorry, 1 minus e power minus x by L into f naught into e by e minus 1. This is my tension as a function of x. Now this is nothing but some constant k times 1 minus e power minus x by L. Can we plot this function? Yes, we can. 1 minus e power minus x by L. When x is equal to 0, my tension is 0. Alright? When x is equal to 0 here, there is no mass which is being pulled. Tension is 0. When x is equal to L, my tension is F naught. Right? That's how tension is varying. Students, if you have got any doubts from the books you are practicing, message it to the WhatsApp. We'll discuss the doubts in the next class. Alright? Do not hesitate to ask doubts. Solve J&D, practice J&D. Whatever doubts you get, you post it in the WhatsApp. We'll discuss in the next class. Alright, I hope this is clear. Now we'll do something else. We'll apply the force at this end now and find the tension as a variation of x. We have applied the force over here and we got tension to be varying as like this. That means when the thicker part is here, It is applied to the thinner part. I got tension to be bearing like this. I will apply the force at this end now, towards left. Now I want the variation of tension with respect to x. All right. Here tension is going on increasing. At t equal to 0, x is equal to 0, t was 0. And it went on increasing from x is equal to 0 to x is equal to L. But when I apply it over here at this end, my tension will be maximum at this end because it will be F0 here and 0 here. So it will drop from F0 to 0. All right. That's what common sense says. Logic says, if I apply it over here, tension at 0 will be F0 and tension at L should be 0. So it should go from F0 to 0 from when I go from x to 0 to L. But here in this case, when I applied force on the right side, my tension was 0 at x is equal to 0 and tension was maximum at x is equal to L. It increased from 0 to L. As I go from 0 to L, my tension increased. But in the next case, tension decreases when I go from 0 to L. All right, let's see how do we do that. Again, I section it. I'm applying the force over here. So I section it like this. Tension Tx, this is origin, this is F0. Tx, this is L, this is x, this is x, this is 0. Now acceleration will be towards left at the same acceleration. Whatever acceleration we got before, we'll have the same acceleration. So I can either use this one or this one. I'll use this one because there is no F0 over there. It's easier to handle here because I will not have to write F0 minus Tx is equal to mass into acceleration. Whereas I can directly write Tx is equal to mass into acceleration. So Tx is equal to mass times acceleration. What is the mass now? Integral x to L e power minus x by L Tx into acceleration. What was the acceleration we got, students? F0 by lambda naught L into
1
1
minus 1 by
minus 1 by E.
right. Right, that's it. Is that correct? I hope that's correct. All
Yes,
right,
sir.
now let's further simplify it. All right, it's correct. Thank you. So this integral would be e power minus x by L by minus 1 by L under limits x to L into this acceleration A, which is substituted at the end. Now I remove this negative sign and I flip the limits. And I've got A here, so this L gets cancelled out.
L can
Yeah. Can you further simplify this and tell me the last expression? Tx is equal to e power minus x by L minus 1 by E into f naught E by lambda naught into E minus 1.
lambda.
Okay, now let's see. Let's substitute x is equal to 0 and see what is happening. When I substitute x is equal to 0, I'll get e power minus 1. Sorry, 1. 1 minus 1 by E is 1 minus 1 by E is cancelled out. And what happened to lambda here? Lambda is cancelled out, right? Lambda naught here and lambda naught here, lambda naught is cancelled out. So you'll not have lambda naught here. So when x is equal to 0, I'm getting Tx to be equal to f naught. When x is equal to L, let's see what's happening. When x is equal to L, I'll get 1 by E minus 1 by E is 0. So I'll get T equal to 0 when x is equal to L. When x is equal to L, I'm getting
Sorry, x is equal to 2. X is equal
when
to
x is
4.
equal to 0, it is f naught, x is equal to L, it is 0. Now to plot this function now. How do I plot this function? If not,
Sir, the curve will touch the x-axis.
what is it? What you said? Sorry, that's a very
The-
good point.
Is the
Curve
curve
is
touches the x-axis?
Curve?
x-axis.
X-axis touches us, sir.
That's a good point. See, what is happening here is, ఇలా అనుకున్నావు కదా?
Yeah, sir.
Yes.
But see, what is happening is, I was about to tell that. That's a very good question, Vignesh. See, what is happening here is, I'm getting some constant times e power minus x by l minus some constant c, right?
Yes, sir.
So f of x minus c. So if my f of x is like this is my f of x. Minus c would be, I pull it down. So that asymptote is somewhere here. ఆ asymptote కిందకు వచ్చేసింది. Asymptote which was x axis before, ఆ asymptote కిందకు వచ్చేసింది. అందుకే x axis కి intersect అవుతుంది ఇది. And that makes sense also. See, because it has to intersect x axis, because x is equal to L, my tension should become 0. If it is asymptotically decreasing to x, my tension is never becoming 0. But whereas practically tension is becoming 0 at this point, right? So that makes sense physically also. But mathematically, what is happening? When I pull this function by constant some c downwards, some e power, let's forget about this k, e power minus xl, x by l minus c would be, this would be c units downwards. So e power minus x ఇది ఉంది. E power minus x ఇది పైన the curve. Minus c would be lower curve. This x-axis asymptote, which was x-axis, is now shifted to y is equal to minus c. Asymptote shift అయిపోయింది. అందుకే అది is tending to 0 or it is tending to minus c as x tends to infinity. It's not tending to 0 now. X-axis is not my asymptote now. Do you get the difference, Vignesh?
Yes, sir.
So x-axis intersect అవుతుంది. And that makes sense also because it has to intersect x-axis because at certain value of x, which is L here, tension has to become 0. So this part of the curve doesn't make sense. Tension negative doesn't make sense because there's no mass there. So this is my variation of tension. All right. Try plotting this curve. You'll understand this better. All right. I just plotted using 2 points inside an exponential variable decreasing up to then plot this, I know. But you can plot it in a better way. F of x తీసుకొని f of minus x చేసి then minus multiplying it with a constant, then pulling it down with a constant. All right. So you'll get better understanding of the plotting of the curve, sketching of the curve. All right. So let's stop here, students. But so evening, we're going to start circular motion because we'll have both the patches. And it was just a revision of these things. This is again required in the rest of the chapter. That's why this is very important. So you should be able to handle integrals in a pretty comfortable way. All right.
Sir, evening timing sensor in physics class.
Class timings evening 7:30.
Okay, sir.
6:30 we'll have Gurinder sir's class. 7:30 we'll have my class.
Okay, sir.
All right. Or it may swap also. We are not sure. All right. You will have Kevin sir's class as well today. All right. So depending on, you will have class from 6:30 to 8:30. Yeah, that's it. Be there in the class. Like whatever subject you have to attend. All right. Thank you all, students. Have a great day. Bye, everyone.
Hi, sir.
Bye everyone, students. Again, we will meet in the evening from 6:30 to 8:30.